So what I couldn't finish last hour because of lack of time. How about higher order modes? The larger the waveguide, the more modes are available. The condition is at very low frequencies. This thing doesn't work because I need lambda quarter here and lambda quarter here. Otherwise, I have no transmission line in between. So every waveguide mode will have its own cutoff frequencies. How is defined the cutoff frequency? Well, we can look at this equation here. So this is fixed by the dimension of the waveguide. This is frequency. Frequency divided, or I could write it also here. This thing here is omega divided by C0. This is omega divided by C0, by the speed of light in free space. This is frequency, and now beta is the question. We should get actually a positive beta squared for this equation because we need a real beta here. In order for the beta to be beta squared real or beta positive, we define when is this going to happen, when beta is going to be 0. So cutoff of the waveguide will happen when beta is equal to 0. So when m times p over a squared is equal to k squared is equal to omega, sorry, all this squared here. I forgot the squared sign here before. Just, I was thinking just k, not k. I should square this thing here. So omega squared over C0 squared, or m times p over a is equal here to omega over C0. Or, written with the frequency, this is 2p f frequency divided by C0, okay? And we can cancel out now if we are looking just for the frequency. The frequency now is cutoff frequency or omega cutoff frequency. I'll write cutoff here. Cutoff frequency is now, if I go p cancels out, so it's m, it's half. If it is C0 over a. Hope I wrote everything down correctly. So 2 goes here, p goes in the denominator, cancels out, a stays where it is. Okay, so now we know what the cutoff frequencies are. For this first example up here, our cutoff frequency f01 is now equal to what? M is equal to 1 is C0 over 2a. Or in other words, what is the cutoff wavelength? Let's say lambda 01 is now just C0, sorry. This F0 is also, I can rewrite this thing as C0 over lambda cutoff, lambda 01. And now I see what lambda 01 is. Lambda 01 is 2a. So the wavelength should be less than, the frequency should be higher. Frequency should be higher than this, or the wavelength should be smaller than 2a. Okay? This is the condition for the cutoff for the first mode. For the F02 is now, here I have the number 2, so it's 2 times C0 over 2 times A, is now C0 over A, or lambda 02 cutoff is now equal to A. or wavelength should be smaller than A. And for the final example I have here, for the mode with the other polarization, F10 is now equal to C0 over 2B, because I have B in the x direction. Now it's this, and this is, from this I get that lambda 10 is now, the cutoff wavelength is now equal to B, 2B, if I do 2B here, or lambda should be smaller than 2B. I make so many mistakes here that 2B, and I may rewrite also this thing here because it's not clear on the bottom. 2B. So what I know about now about the sides A and B. I am, in which range am I single mode? I am single mode only in a limited range of frequencies, so the frequency should be larger than F01 and smaller than F02. I know what F01 is. This is C0 over 2A, and this is C0, speed of light, over A. So in the frequency range 1 to 2, I'm single mode. And now what choice makes sense for the B here? It makes sense that this thing here is equal also the F10. This is equal to C0 over 2B. It makes sense. So to have the broadest possible waveguide, A should be 2B. So, or B should be A half. And this is true for most waveguides. Say, for this waveguide here is true. This thing is true. It's also true from this waveguide here. The sides here are in the ratio 1 to 2. It is not true for this waveguide. This waveguide here is, this is 0.9 inches and this is 0.4 inches. It's about 1 to 2, but it's not exactly for this waveguide here. Just to explain you how waveguides are chosen. So what is the maximum directivity we can get out of this antenna if we want to avoid higher order modes? If I want to avoid higher modes, A has to be less or equal than lambda, and B has to be less or equal than lambda half. Okay? So our maximum directivity is now what? Our maximum directivity is now 4p over lambda squared. Then I have the illumination efficiency and I have the area. And it is 4p over lambda squared. Illumination efficiency is 8 over p squared. And further I have area A is lambda is A times multiplied by lambda half is B. So it's lambda squared divided by 2. So what is the maximum directivity I could get out of this antenna? Let's see. 4 times 8 is 32 divided by 2 is 16. Lambda square cancels out. What I can get out of this antenna? P over p squared is p in the numerator. So this is approximately, how much? This is approximately 5. P into 16 goes about 5 times. So this is approximately 7 dBi. 7 decibels of gain I can get out of this, where I have my illumination efficiency. I forgot to write this before. 81% is approximately minus 1 dB. I lose 1 dB for the non-uniform illumination of this aperture, and the largest aperture I can afford without incurring into higher order modes is this lambda A and lambda half B for conventional waveguides. So this is what I can do with just a single waveguide. Now, how to get to higher gains with a Horn antenna? In order to get to higher gains with the Horn antenna, I should make the same illumination of a larger area. So what am I going to do? I'm going to take this initial waveguide I had here, and I'm going to gradually increase the size of this aperture to get a much larger aperture here. So if this transition is smooth, I avoid generating higher order modes. So this is my original waveguide, sides A and B. Now I could write these sides width and height here. These are much larger, so width is much larger than A and height is much larger than B. But if I make a smooth transition, I'm not going to introduce new modes. And these smooth transitions, I have two examples here. How are they done? So this is a waveguide horn that has a very, very smooth transition. Also, this one here, this one has the transition, also already the waveguide to coaxial cable to waveguide transition, and then we have this horn that is slowly increasing. So if this thing is long enough now, and how much long it has to be, then I should be able to obtain also higher directivities, higher effective areas here, with still the same illumination efficiency, approximately that's the size. So where is the limit with such a horn here? The limit with such a horn is that inside the horn, the waveguides are, the wavefronts are spherical. And we already dealt with this problem with the spherical wavefront. How to avoid errors when wavefronts are spherical? Spherical wavefronts could be represented also by higher order modes. But I need to make the horn in such a way that these wavefronts will be flat here. Okay, what is the condition now here? Well, we already had the Rayleigh distance is the condition. The Rayleigh distance is the condition, so our length of the horn, L, the horn should be long enough in order for this thing to work. So if you remember from 2 weeks ago, this length of the horn, this L here, should be larger or equal than 2d squared over lambda. This is for a phase error delta phi below or equal to P8. Okay? This was for the smaller, this was the Rayleigh condition. Or Fraunhofer condition for the far field. It's exactly the same thing as the far field of an antenna, but here we are moving actually inside an antenna, but it's exactly the same problem. Exactly the same thing we are talking about. So let's see, and this d squared, what is d squared now? According to Pythagoras, d squared is a squared plus b squared. Sorry. Not the original waveguide, but the aperture, so w squared plus width squared plus height squared. Okay? we know what we are talking about. What are now the conditions, say, for this thing? Let's try a simple example. Example for a satellite TV antenna. We want an aperture that is W times H, that is half a meter times half a meter. Dot time half a meter. This makes sense. So now W is half a meter and H is also half a meter. This approximates the size of a satellite TV dish. What length of a horn do we need if we want to avoid phase errors? To avoid here having spherical wavefronts here. We calculate now what is d squared. D squared is now W squared is 0.25 meters squared plus H squared is 0.25 meters squared. This is now half a meter squared. Okay? And satellite TV antenna that operates at a wavelength of 2.5 centimeters. This is frequency of 12 gigahertz for satellite TV. Okay? Now let's try to calculate what is the length. Length is larger or equal than. We have 2 times 0.5 meters squared divided by 0.025 meters, okay? This is my wavelength. So, if I calculate this thing, this is 1 meter, squared and meter cancels out, divided by 0.025. This is equal to 40 meters. Now I hope you understand where the problem is. This horn, in order to keep the wavefronts flat, not to having spherical wavefronts, this horn has to be now very, very long. So this horn, starting from our waveguide, this horn here has a square aperture here. But this horn that has half a meter aperture times half a meter should be here 40 meters long. This is not a practical antenna. It works. Everything in the theory is okay. Just where did we get to troubles? We got to troubles with our request, our very stringent request for the phase error. This very low phase error here means that this very small phase error means that we need a very, very long horn to achieve wavefronts that are flat enough to not to lose any directivity or any gain because of phase errors. So you see that this is not practical. So what is the conclusion out of this discussion? Horns always work. Whatever kind of horn do you make, it works as an antenna. But it may be a very stupid antenna. You may need lots of material for very little decibels, for a few decibels of gain. So that's the problem with horns. Okay, you may make longer horns. Like this one is a little bit longer. If I can pull it out. You see that this thing gets pretty long. For not such a large aperture, consider the frequency band. This is about 15 gigahertz, so it's 2 centimeters wavelength. 2 centimeters wavelength, you see, you get already a long horn. Let's try to be more practical. What can we say about the Rayleigh distance? Certainly, this thing here was an overkill. This was an overkill requiring so many, such a small phase error. We could make a less stringent requirement, losing a few fractions of a dB of gain, but building our horn much shorter, so using much less material. And now there is a practical consideration. What length of horn should we use? And what phase error should we tolerate to use the least amount of brass sheet or aluminum sheet to make a certain amount of decibels of gain? So, because if I make the horn too short, I have huge phase error, and that kills the gain. If I make the horn too long, I need a huge amount of aluminum sheet. So we have to find a compromise, and quite a good compromise is to go this phase error to go below pi half. This means minus 1 dB of gain, minus 1 dB of gain. If we go to pi half, so this is in, so our length here should be now larger or equal than, here we have 2 lambda, now we have 2 in the numerator, and in place of lambda, this thing should be satisfied in the E-plane, in the plane of the electric field. So this is height. This is height. So height squared. And here I lose minus 1 dB. And in the other plane, in the H-plane, in the E-plane, we have a constant field. In the H-plane, I have a cosine of pi over w times y. In this constraint, I can use a slightly less stringent requirement for the phase. The phase error should be smaller than 3 pi quarters. Slightly more, and this also gives minus 1 dB. Why? Because of this distribution. You see, this distribution in the H-plane, this distribution in the H-plane, you see, you have very little field here, very little field here. So this field that is very small, it doesn't really matter that it has, this small field doesn't really matter that it has a large phase error, because it's not going to count much in the final result rather than this field here. While in the other dimension, in the E-plane, I have a constant field, and in E-plane, every single point counts the same. So here I may have a less strict requirement for the phase error. So L is now larger or equal than what? Larger or equal than 3/4 is now h over, no h, but it's somewhat, so I have w squared over, so if the phase error is allowed to be larger, then I think here it's 3 lambda. 3 lambda, I hope I didn't make mistakes, to have this allowed this larger phase error. So this is, I could call this optimal horn. Optimal horn that loses minus 1 dB in the E-plane and minus 1 dB in the H-plane. So in total, this optimal horn, you see, how do I calculate? I can invert this, these expressions. for given L what I get for W and for H. And you see that most horns are rectangular. They are much narrower in the E-plane because the E-plane is constant. In the E-plane, the field is constant. And they are much wider in the H-plane because in the H-plane I have the maximum of the field here, and field decays here, and field decays in this direction here. So I can work with larger phase errors here. So what is my calculation now? Here my illumination efficiency is going to be approximately -1 dB for the waveguide. That has a cosine of pi a over y. And then I have -1 dB in the E-plane, so phase error in the E-plane. And I have a -1 dB for the phase error in the H-plane. So in total, I have approximately -3 dB, or the total illumination efficiency of such an optimum horn will be about 50%. And this horn here is almost exactly, this horn here is such a horn. An optimum horn that has some phase error, some finite phase error, but brass is expensive, so we tried to get the maximum number of decibels out of this brass, and this horn comes up to about 22 dB of gain, of directivity, this horn here, at the center frequency of 15 gigahertz. Here. Of course, if the aperture is smaller, we can make shorter horns. Like this horn here, because it operates at a lower frequency, this is a 10 gigahertz horn, can be made much shorter, and this is still an optimum horn, also this one here. For special purposes, if we want unsymmetrical radiation pattern, we may have horns that only open in the E-plane, like this one here, you see. So let's take two identical ones. Okay, this one. This one is the one that matches. So both these horns are for 10 gigahertz, same waveguide. Waveguide oriented now for vertical polarization. Waveguide. So this horn is open in the E-plane, only opens in the E-plane, and this horn here only opens in the H-plane. So this one will have a narrower beam in the E-plane because it has a wider aperture, and this horn will have a narrower beam in the H-plane. These two are for 10 gigahertz. I have also for 15 gigahertz the same story. If you see this waveguide flange is a little bit smaller because it's for 15 gigahertz. I have the E-plane horn with a narrow beam in the E-plane. I have an H-plane horn with a narrow beam in the H-plane. Narrow beam in the H-plane. So I can play with these things by changing the horn. But if I want the maximum number of decibels, then this thing has to be rectangular with a certain ratio of these sides. The ratio of the sides of the horn may range from W towards H may range from 5 to 4 up to 4 to 3. So this is optimum horn. This is really not 5 to 4, this is really square root of 3 against square root of 2. But it's about 5 to 4. And this is a symmetrical main beam. In this way, I obtain a rotationally symmetrical main beam with a 4:3 ratio of the two sides of the horn antenna. So this is about the design of the horn. What about the radiation patterns of horns? Well, if I draw the radiation pattern of horns, and let me draw the radiation patterns for the horns that have symmetrical beams, even though the optimum horn is very close to this. It's not much difference really here. It's not much difference. What ratio should I use? So if I write here the angle theta, and if I draw here the radiation pattern, and I intend these horns radiate, they still have their maximum if theta is 0. So what kind of beams do I get if we don't have this time today to make the whole calculation? What kinds do we get? In the E-plane, I get a beam. You may remember last time when we did the calculation. So this beam was the shape of sine of u over u, if you remember the calculation from last time on the lectures. And this is for the E-plane. Where this first side lobe is at minus 13 dB. For the H-plane, I do not have a constant distribution. I have a constant illumination in the E-plane. In the H-plane, I have a tapered distribution, and this will provide much lower side lobes. So in the H-plane, it's a very lengthy calculation, but these side lobes are much smaller. So this is about minus 25 dB, if I remember correctly. This is very low. In the H-plane, I have much lower side lobes. If I did all the integration of the radiation pattern, you may remember last time we did it, but it's a lengthy integral. I certainly am unable now to do it in 10 minutes. So this is very low. If I look at the measured radiation patterns of a symmetrical horn like this one, this will provide almost symmetrical pattern. I can simply separate between the E-plane and H-plane. See, the horn has huge side lobes in the E-plane. Has large side lobes because of the constant distribution. But in the H-plane, because of the cosine distribution, the side lobes are much lower. So in the H-plane, this way, this is E-plane is this way. If you look at the waveguide, E-plane, electric field is in this direction. E-plane, in the E-plane, the radiation pattern has large side lobes. But in the H-plane, the side lobes are much lower. There is yet another thing we should discuss. All these horns actually have phase errors. This one has small phase errors. This one has larger phase errors. This one has quite small phase errors because it's very smooth. It has a very smooth transition, so this is not so bad. Okay, we can also build horns from circular waveguides. Okay, this is also a possibility to be done. So what happens if I have a phase error? And now for the phase error, I will try to draw the same plot, but here theta, off axis, angle, and here I will draw the logarithm of the radiation pattern. Okay, I have to take the absolute value for the radiation pattern. Also here it would make sense to take the absolute value. On a logarithmic scale, how do things look like? On the logarithmic scale, I may see better what is going on. It's the same radiation pattern drawn in another scale. And this is now the minus 13 dB point for the E-plane. Now, what happens if I have a square phase error? So E-plane plus a significant square error, delta-phi. The radiation pattern will not change much. The radiation pattern, only the minima will become shallower. But the radiation pattern, you simply don't see any difference. Only the minima here become shallower. And only when you have large phase error, then you see some decrease of the main peak, and of course shallower minima. Oh, sorry, it was not accurate. So minima tend to disappear when you increase the phase error. Also here I have some loss of forward gain. Well, at small phase errors, I only see that minima become shallower. The peak really doesn't go down that much, so this minus 1 dB point is right in between here, the green and the blue figure. The same happens with H-plane. So if I draw here an H-plane with a large phase error, not this. Practically all minima and maxima here disappear. This thing simply goes down, and some way like this. So this is H-plane. Plus phase error, plus delta-phi. In the H-plane, I seldom see any side lobes in the practical measurements because of this. This is only for the theoretical distribution, illumination with no phase error at all. I can also do the similar things as I did here with rectangular waveguides. I can do with circular waveguides. And I showed you some examples here. So these are two horns made from a circular waveguide. This one here and this one here. So with the circular waveguides, I also have higher order modes. I should get some space on this table here. With circular waveguides, I also have higher order modes. And of course, if I have circular geometry, everything is related to Bessel functions. That's typical. So, for a waveguide of circular cross-section, I may have the fundamental mode, and the fundamental mode, the field of the fundamental mode, TE11 is like this. I draw just the electric field lines. So this is TE11. And next higher mode is TM01. TM01, that looks like this. The electric field goes radially from the center of the waveguide. While here, this mode is quite similar to the fundamental mode in the rectangular waveguide, and its cutoff frequencies, so frequency TE11 is now equal to 1.842. This is the Bessel function divided by 2 pi a. times C0. While the F for TM 1, 2, 1, 2, I forgot 1, 2. TM 1, 0, the frequency is slightly higher, 2.4049 to pi A, where A is the radius of the waveguide. A is the radius, just. So A is the radius of the waveguide, or here A is the radius. Waveguide. Times C0. If it's free space inside the waveguide, so hollow waveguide without dielectric, then we have speed of light here. So we have these two conditions for the, let me write once again because this is not nice here. This is not nice here. 4, 1, 2, this is the maximum of the J1, and this is the 0 of J0, the Bessel functions. Also here I have quite a restricted frequency range. So what you can do about this, you can build actually simple antennas, and these are two simple antennas built by students. The so-called coffee can antenna. You need a coffee can. What size? Approximately radius 5 centimeters. Here times 2 pi times 12 is about 24 centimeters. 1.8, you get the correct wavelength for Wi-Fi. So, if I want to build a Wi-Fi antenna, for the frequency of 2.4 gigahertz, I should only excite this mode, and I should not excite this one here. Okay, so my frequency should be larger than the fundamental mode cutoff, larger than FTE11, and smaller than the frequency of the next higher order mode, FTM01. How do I build this antenna? I take a coffee can. So here it's open. This is the aperture. This is closed. So it's closed. And I install here my probe to excite the desired modes. So this probe that has the capacitance to the other end, up here, it has some inductivity over here. So this is the trick to get from a 50 ohm standard coaxial connector, 50 ohm, to fit the waveguide. And of course, what I should not forget here, that here at the open end, I have some reflection. I have the reflection. This gamma is different from 0. So this reflection will also affect a little bit the impedance. So it's a little bit tricky to get all the dimensions from a standard coffee can to get good impedance matching. But I believe your students have the time to do that. And if you build such an antenna, I give you 1 grade more at the final exam. So the prize is 1 grade more at the exam. In the final, if you build such an antenna, not necessarily the coffee can. Everyone sees the project for the coffee can on the internet. Which coffee brand do you have to buy, which matches the dimensions of the Wi-Fi the best possible way, and then build these antennas. Next hour, I will show much more interesting antennas you can build at home. Okay. So they are a little bit more fun than drinking coffee. Coffee is not good for your health anyway. So let's see next hour.